Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 24, practice session number 6, in which we will solve our next problem that deals with an elegant and an exquisite mechanism known these days as the Peaucellier-Lipkin linkage. As a very short historical exposition and in the lightning round, the immediate development of the mechanical device that we will study in this episode unfolded as follows. In the private letter in the year of 1864, the gentleman by the name Charles Nicolas Peaucellier, who lived between the years of 1832 and 1913 and who was an officer in the engineering arm of the French army, described the invention of a device that can convert a circular motion into a linear motion, but he did not take his idea any further, meaning he never published his discovery officially yet. Separately, and several hundred miles east, with respect to where Mr. Peaucellier lived, the Russian mathematician Pafnuty Chebyshev, who lived between the years of 1821 and 1894, had a student who went by the name Peaucellier-Lipkin, who lived unfortunately a very short life of 36 years between 1840 and 1876. Now, this student of this mathematician published his paper in 1870, so 6 years after Mr. Peaucellier made his claim about the invention of this device. And in his paper, Mr. Lipkin described the mechanics and the operation of this device in great detail. And only 3 years after that, Charles Nicolas Peaucellier publishes his paper in 1873, in which evidently he references the paper by Mr. Lipkin. Before we deep dive into the mathematics of the Peaucellier-Lipkin linkage, we need to settle on a matter that is so important that I carried it out into a title of a separate segment. And that idea is the following. Ever since the Scottish engineer and the chemist James Watt, who lived between the years of 1736 and 1819, invented a better steam engine, there emerged an interest among the engineers in constructing or inventing or discovering a mechanism that could convert a circular motion of one link joint into a linear motion of another link joint, and such a device that converted basically circular motion into a linear motion had to have at least 3 properties that are listed over here. Such a device needed to be robust and rugged, in other words, not easily breakable. Such a device had to be simple in its correct operation. Again, it is known from practice that the more complicated a device is, the more moving parts it has, the more delicate in some sense it becomes, and more chances for this device to misbehave or to not operate correctly. So we want a device that is as simple as possible, but not simpler. And the third, such a device had to be compact, which in mechanical engineering basically means that it had to be planar in its overall configuration, which again, intuitively speaking in plain English, we should be able to take such a device and slug it in to a very thin box. Now, at a time, the existing such mechanisms suffered from the following 2 drawbacks. Their conversion of the linear motion, circular motion into a linear motion was only approximately linear. This conversion was not a mathematically precise operation. That's number one. And number two, the range of motion over which the conversion was approximate was small, or the amplitude of motion over which the linear approximation of a circular motion was very small. And if you studied any form of mathematical analysis or differential calculus, for example, you know that the first derivative of a function at a point, if the function is differentiable at that point, is what is the best linear approximation of the function at that point. But for that best linear approximation to work, the whole business has to revolve around very small sizes. And one of the reasons why the Peaucellier-Lipkin linkage carries a historical significance is because apparently it was the first device that addressed both of these drawbacks of the converters that existed at the time. The Peaucellier-Lipkin linkage was exact in its operation. In other words, it did not produce an output approximation of a straight line, but its output was a mathematically precise straight line, and we will see in a minute why was that. And number two, that linkage was planar in motion. And once we understand how, not only how it works, but why it works the way it works, we will see that it is theoretically applicable to any range of motion, not necessarily the small range of motion. And again, before we move on to the underlying mathematics, and that is why I branched out this discussion into a separate title and to a separate segment, we need to understand what does it mean that a mechanical device is planar. It should be understood that any intersection between mathematics and something in real life, whether that intersection is called physics or mechanical engineering, takes place over a device known as a mathematical model. A mathematical model. And for example, in physics, such a model is a collection of presumably observations-based axioms, which, when coupled with the formal rules of mathematics, most notably the if P then Q implication, becomes what in physics is called a formalism. For example, a Newtonian formalism, a Lagrangian formalism, or a Hamiltonian formalism. And at that point, mathematics completely takes over and produces its results inevitably, so to speak. For example, based on the famous theorem due to Emmy Noether, any physical system that possesses a continuous symmetry has a certain quantity that is preserved. And more specifically, any physical system that possesses a continuous symmetry over time. In that system, the law of conservation of energy holds. In other words, that preserved quantity is energy, and any physical system that possesses continuous symmetry over space possesses the law of conservation of momentum. As such, the indoctrinated viewers of our channel already know that physics is an exact solution of an approximate problem. But mechanical engineering is, in plain English, an approximate solution of an exact problem. So in that sense, physics and mechanical engineering are the inverses of each other. But even in mechanical engineering, all the designs of all sorts of devices and mechanisms is still based on the idea of a mathematical model. And pertinent to our discussion, the links that we will be discussing in this episode are modeled. This is important to understand. The links are modeled with line segments in our case, but these links can also be circular, elliptic, parabolic segments, or whatever other shape is needed on that case. And the link joints, or the places where one where two or more links are put together, they are modeled or logically replaced with their equivalent. That is called the center of mass of a joint, and the center of mass is modeled with another mathematical abstraction called a point, and it should be understood that in real life no single mathematical object exists. In real life there are no mathematical points, mathematically precise circles, mathematical straight lines, planes, spheres, cubes, paraboloids, or whatever other mathematical object you can pick. There are no prime numbers, there are no integrals, there are no derivatives that exist in real life. Everything that we think of when we design something, we operate in terms of pure and abstract mathematical objects, which when put together become a model, and based on such a model, a physical device such as the Peaucellier-Lipkin linkage is produced. In its classical configuration, the Peaucellier-Lipkin linkage consists of 6 rods and 5 link joints. Again, because in this episode and on this channel we operate in terms of mathematical models, the number of rods in the Peaucellier-Lipkin linkage is 6, but in the practical or physical implementation of such a linkage, there will be another rod or another link that connects the point C with the center of the generating circle S, but we will get to it in a second. Again, because in this episode we're interested in the mathematics of the underlying mechanism and not its physical implementation, we omit the 7th rod, which is, or the 7th link, which is technically present in the actual implementation of this device. And these 6 links or 6 rods are configured or put together as follows. The first 2 rods are the line segments OA and OB. If you can distinguish colors, then these rods are shown in green, and both of them have one and the same fixed length L, depicted over here. The distance from the point A to the point O is L, and the distance from the point B to the point O is also uppercase L at all times. The next 4 rods are shown in red, if you can distinguish colors, and they also have the same fixed length at all times, which we stipulate is strictly smaller than the length of the green rods OA and OB. These links are AC, AD, and BC and BD. And evidently we model all these links with absolutely rigid bodies, which means that the distance between any 2 points on such a body remains one and the same at all times during the motion. Now, the rods OA and OB are positioned in such a way that they're linked together at the point O, but the point O is fixed. And the point C in the classical Peaucellier-Lipkin linkage executes its motion over a generating circle, lowercase s. This is what I depicted over here. The point C runs along an arc that belongs to a circle S, and the point O that is fixed also belongs to that circle, lowercase s. We take it that the radius of the generating circle, lowercase s, is known to us. It is an uppercase R, and all the joints in the Peaucellier-Lipkin linkage, all the joints are movable. Now, in the traditional implementation of this linkage, the input power is applied to the point C, and the output of this device is the point D and its trajectory. In other words, the input power is applied to the point C in such a way that the point C moves along an arc of the parent circle S, and that arc, as we will understand momentarily, definitely does not pass through the fixed point O. And during its operation, all the joints are movable, as I said, which means that as the rods, for example, OA and OB move, then the distance between, like I said, the points A and B to the point O, they remain the same, L evidently, but the distance between the points A and B can vary over time during the normal and intended operation of the Peaucellier-Lipkin linkage. What other distances can change and which other distances remain fixed? Well, it is evident because the smaller rods shown in red of length lowercase l are rigid. The distance between the point B and C does not change, it remains the same. The distance between the point B and D remains the same. And the distance between the point A and C and A and D, these distances remain the same, but the distance between the points C and D will vary, it will change. The distance, like I said, between the points A and B will vary. Will the distance between the points C and O vary? Yes, of course it will, as the point C deviates from this, let's say, position of equilibrium, where the points C, O, and the center of the parent circle, lowercase s, which I did not show to avoid the clutter, are collinear. But then as the point C deviates from this position, it gets closer and closer to the point O, and at some point, again, purely theoretically, this point can coincide with the point O, at which point the distance between these points is evidently zero. And now we can understand what does it mean when in the previous segment I claimed that the historical significance of the Peaucellier-Lipkin linkage is based on the fact that this mechanism was the first planar mechanism that produced mathematically precise conversion of the circular motion of the point C into the linear motion of the point D. That means that if we replace, of course, the physical implementation or the physical objects that make up the physical incarnation of this mechanism with their mathematical objects during its normal intended operation, all the objects at hand, shown over here, which is a model of the physical device, will remain in the parent plane. And in some sense, we can even go as far as numbing down the geometric sensitivity of this mechanism a little bit by replacing the material line segments of length uppercase L and lowercase l with what? With their centers of mass, which are modeled with the point. And then we will have what? We will have one point is fixed, it does not move, it's somehow in the physical implementation, it will be attached to a frame or to a base of some sort, or whatever the case may be. But the points A, B, C, and D. So we have 4 points that execute some sort of motion, and to this 4 points, each of which represents what? Each such point represents the center of mass of the corresponding link joint. For example, the point A represents the center of mass of the joint of 3 line segments, AO, AC, and AD, and so on. The point B is the model of the center of mass of the physical link joint between the links BO, BC, BD, and so on. So how many such centers of mass we will have? Well, because we will have 6 rods, we will have another 6 points, each of which is the center of mass of the corresponding material line segment. So altogether we will have 10 points in this particular case. And when the Peaucellier-Lipkin linkage operates in its correct and intended fashion, all 10 points belong to one and the same plane, ambient plane, let's say pi. This is the overall description of the Peaucellier-Lipkin linkage device. And now that we understand what does it mean to be planar, again, it's a mathematical abstraction. The physical device, of course, is not mathematically flat, so to speak, because in real life there are no mathematically precise planes, spheres, and so on. So this is an approximation, or what we have on board over here is an idealization of the physical reality, but based on this mathematical model, the operation of this device is mathematically precise. And again, the claim is that if in such a configuration of the relevant mathematical object, the input power is applied to the point C in such a way that the point C traverses an arc of the parent circle lowercase s, the output point, let's say D, will trace a mathematically precise straight line. And in order to show you a visual confirmation of this claim, I have put together for you an animation using the free software called GeoGebra. And in that animation that you will see in a few seconds, everything is rendered quite faithfully. The only thing is that with this animation, I'll give you a chance to test your visual mathematical intuition and see if you can spot what is going on in this configuration. You will see that the point C will run along an arc of a circle S with the point A fixed, and initially you will see the point D without the tracer on moving about in the plane somehow. See if your intuition tells you that yes, the point D definitely traces a mathematically precise straight line. But then a few seconds later, I turn the tracing mode for the point D on, and at that point you will see that the point D traces a line segment that belongs apparently to a mathematically precise straight line. Now that we understand what a Peaucellier-Lipkin linkage is, how it operates, and what it claims to do, we can move on and put together a statement of the problem number 25 of this course. Which is, show that under the given configuration of the input object shown on the left side of your screen, if the point C moves along an arc of a circle S that passes through the fixed point S, the trajectory of the point D will be precisely a segment that belongs to a straight line. For a change of pace, we will first generate the relevant proof that we are required to generate in this problem, pretending that we know absolutely nothing about inversive geometry. And one way to show that the point D traces a line segment that belongs precisely to a straight line is as follows. Due to the symmetry of the Peaucellier-Lipkin linkage, we can claim that the motion of all the points that can move in that linkage, the points A, B, C, D, they of course execute a so-called finite motion. The point C traces an arc of a circle that passes through the fixed point O, but that motion within its range, within its legal range, is continuous. And that means that at some point, as the for example, the arm OA swings logically downward, or as the arm OB swings upward. You saw in the animation, these two arms can move independently of each other in some interesting way. they will pass through the position, let's say, logical equilibrium. And logical equilibrium means that if we take our generating circle lowercase s, we take our favorite fixed point O, and through that point O and the center of the generating circle S, which I do not show in order to avoid the clutter, we snap a straight line, then at some point the joint C will hop precisely onto this diameter of the generating circle S, and the points O, the center of the generating circle S, and the link joint C will be collinear. Now the shape A, B, C, D at all times is what? It's a rhombus, because the length of the sides of this shape, they remain not only constant but equal to each other at all times. And we know that the diagonals of any rhombus intersect at what? At right angles. And that means that in such an logical equilibrium position, the diagonal CD of our parent rhombus and the diagonal AB will intersect at the point M, such that, let's depict it over here. So we will have the line segment AB intersect the line segment CD over the point M, such that the distance CM will be the distance MD. We will call that distance X. We will call that distance X. And the angle over here at the point M, evidently, no matter which angle we pick, that angle will be right. So the idea over here is the following. We catch our incarnation of the Peaucellier-Lipkin linkage in its motion in such a way that it is in the position of logical equilibrium depicted over here. And in this case, the point D has a well-defined certain position. Then we will swing the whole contraption into an arbitrary position that is displaced from its position of logical equilibrium. Somehow we'll introduce a certain angle, and then the overall idea is to show that the projection of the point D prime, the point D will move some location, but the position of the point D prime will be such that the point D will be exactly its the projection, the orthogonal projection of the point D prime will be precisely point D, and that will prove that the point D traces a line segment that belongs to a mathematically precise straight line. And the way to manufacture that proof is as follows. Let us consider the right triangle. Which one is it? OMA. This triangle is right because precisely of the fact that the diagonals in any rhombus intersect at right angles. And then from this triangle, by the Pythagorean theorem, we have what? For the hypotenuse, OA squared, we will have the sum of the following squares: OM squared plus MA squared. But the distance OM over here is a composite quantity, and let us now throw all the names that we have for the material shown in this equality. So in other words, OA is L, so we have L squared is equal to the distance OM is a composite quantity. It can be expressed in many ways, like the distance OD or OC. Here we take it as a sum. We partition the line segment OM into line segments OC and CM. The distance OC, let's put it down over here maybe. So the line segment OM lengthwise will be the sum of the line segment OC plus the length of the line segment CM. But the line segment CM-MC is X, so we will write down as follows the following expression: 2R. This is evidently in this position. This is the diameter, A diameter of the generating circle S. So here we have 2R plus X squared plus, what else? How can we represent the distance MA? We have another right triangle, the triangle CMA, and in that triangle, the square of the distance MA the square of the distance MA from the right triangle CMA. CMA, we have for the square of the distance MA, we will have L square minus X square. You see, this is the distance. MA squared, the side of this smaller right triangle, and for the square of the distance, what do we have? The square of the hypotenuse minus square of the side. The side is CM, CM is X. There you go. So plus L square minus X square. Now, once we open up the parentheses on the right-hand side of the equal sign, we will have 4r squared plus 4rx plus x squared plus L squared minus X squared. Here we see minus X squared and plus X squared cancel each other out. And now we want to isolate X. So we will have 4rx equals L squared minus 4r squared minus L squared. Now 4r, remember, is not a zero under any circumstance. So if we multiply both sides of this relation by 1 over 4r, then we'll have on the left hand side it will be x. On the right hand side we will have L square minus uppercase L square minus lowercase L square divided by 4r minus 4r squared divided by 4r will be r. And now that we have this relation 4r expressed in terms of the locally available material, all we want to do is capture the distance OD. And the distance OD, again, is a composite quantity. It is equal to what? The distance OC plus the distance CD. And now once we translate, the distance OC is twice the radius of the generating circle. And what is CD? CD is CM plus MD, our observations, plus 2x. Plus 2x, so we keep rolling. So what do we have? We have 2r plus 2 in the numerator and 4 in the denominator cancel out. So we'll have L square uppercase minus L square lowercase divided by 2r. And we have to multiply this negative 2r, multiply r by 2, cancel, cancel, and now we have it that uppercase L squared minus lowercase L squared divided by 2r is equal to the distance OD. This is the result that we will need in a few seconds, but it's important to understand that we obtained this result in the position which the Peaucellier-Lipkin linkage occupies in the state of logical equilibrium when, let's say, the points B and A are equidistant from the straight line that contains the diameter of the generating circle S. Now let us pretend that we have caught the operating Peaucellier-Lipkin linkage at an arbitrary position that is legal, but random in the sense that it happened at some moment of time, and this randomness is captured in the variable theta. This is the angle which is formed by the straight line that passes through the points O, C prime, and D prime. Again, we took our rhombus and we renamed its vertices into B prime, D prime, A prime, and C prime, because technically the non-prime letters that we used in the previous segment, they correspond to what? They correspond to the position of logical equilibrium, and in this position, not logical equilibrium, we correspondingly have the vertices named with primes attached to them, and the straight line O, C prime, D prime forms the angle of theta with the diameter of the generating circle S, which, remember, passes through the point C, which corresponds to our logical equilibrium of the linkage at hand. Now, in this position, it should be remembered that all the lengths that we mentioned previously, they will remain the same. The colored line segments have exactly the same length. The line segment OB prime and OA prime is still of length L. This is a definition of a rigid body. The distance between any 2 points on such a body during any time in the motion remains one and the same. So the light colored line segments have the same length as in the previous segment. Consequently, the shape A prime, C prime, B prime, D prime is still what? It's still a rhombus. And in any rhombus, the diagonals of such a rhombus intersect at right angles. Consequently, this time with X prime, we will mark the distance between the point M prime and the vertices C prime and D prime of the parent rhombus. What is the point M prime? M prime is the point where the line segments C prime, D prime, and A prime, B prime intersect. So in other words, the line segment A prime, B prime will intersect the line segment C prime, D prime over the point M prime such that the distance C prime, M prime is equal to distance M prime, D prime, and this is our X prime. This is basically the material that we had in the previous segment carried over into this segment almost verbatim with the introduction of this angle theta that is arbitrary or random within the legal motion of the linkage. And the idea now is again to compute the distance OD prime, this distance right here, the way we do it in exactly the same way from the right triangle OM prime A prime, we will have O M prime A prime. We have exactly the same deal. The distance OA prime squared is equal to the distance O M prime squared plus the distance M prime A prime squared. Rigid body L squared. Now the distance OM prime again is a composite quantity. We assemble it from the distance. This distance right here will be the distance OC prime plus the distance C prime M prime squared plus the distance M prime A M prime, this distance right here. Again, what? This is the side of a smaller triangle, right triangle still, C prime M prime M A prime, which is what? The square of L, lowercase l minus the square of X. So it will be plus, let's say, lowercase l squared minus X prime squared. Now, this distance OC prime over here is what? The OC prime. Let's work with this distance. The distance OC prime. Remember that we said that the point C executes which type of motion? Circular motion, or a motion over a arc of a generating circle that passes through the fixed point. But that means that any point that is this, let's say, rotational image of C prime belongs precisely to the parent circle S. And that means that with respect to the diameter, by the Thales' theorem, the angle at the vertex C prime of the corresponding triangle OC prime C will be what? Will be right. Thus, the middle school trigonometry takes over, and there we go. The distance OC prime is OC times the cosine of theta. And what is OC? It's twice the radius of the generating circle. So this will be 2r times the cosine of theta plus, what is C prime, M prime, X prime? X prime. And this whole thing is raised to the second power. So we have L squared is equal to this plus L squared minus X prime squared. Again, open up the parentheses. Uppercase L squared 4r squared times the cosine squared of theta plus 4r cosine theta X prime plus L prime. Why is that? Because plus X prime squared minus X prime squared cancels out, and evaporates. So now what do we have? We need to isolate our x prime. X prime will be, well, let's write it down like this. 4 times r times the cosine of theta, this guy, is equal to what? L squared minus uppercase L squared minus lowercase L squared minus 4r squared times cosine squared of theta. And now the factor in front of x prime, we take it to be non-zero, multiply this relation through by the reciprocal of this number. So we will have x prime is equal to L squared minus uppercase L squared minus lowercase L squared divided by 4r times cosine of theta minus we have 4r cosine theta, 4r squared, so minus r still like this, and we have one more copy of the cosine theta over here. Now we take our distance x prime, which we already expressed in terms of the locally available material, and we construct our distance OD prime, which is what again? OC prime, which is OC prime plus the distance C prime D prime, C prime D prime, which is twice the distance x prime. So what do we have? Remember that OC prime is 2r times the cosine of the angle theta plus twice the distance C prime D prime. C prime D prime is twice x prime. So minus, we'll say minus 2r cosine theta. You see that this will cancel out. Plus, let's write it down over here, plus this term over here multiplied by where is it, 2x prime multiplied by 2. So we will have uppercase L squared minus lowercase L squared divided by 2r times cosine of theta. And this is precisely the distance OD prime, you see. But this distance OD prime can be rewritten which way? This distance can be rewritten if we move this cosine from the denominator of the left-hand side into the numerator of the right-hand side times cosine of angle theta. And this quantity right here is what? Remember from the previous segment, we proved that this quantity is precisely the distance OD in our equilibrium position. I did not draw the previous configuration because the whole thing will be just a mess, but now you understand, precisely because of this relation over here, look at this, precisely because of this relation, the distance OD prime, in the previous case we had the position D somewhere on this diameter of the generating circle as extended. Our point D was right here. But now if we have this relation, the distance OD is equal to OD prime times cosine theta, precisely. So what does it mean? That means that the point D prime is an orthogonal projection of our traveling point D onto the straight line that passes through the fixed point O and the center of the generating circle S. And that precisely proves that, because remember, we picked this angle theta at random within the legal boundaries, of course, as the Peaucellier-Lipkin linkage operates and weaves its magic. Then within these legal boundaries, the position of the point D prime, which comes out also legally random, satisfies this relation, and that precisely means that the point D travels along precisely, not an approximately, but precisely a straight line, and we can even predict what is the location, what is the position of that straight line. That line must be orthogonal to the straight line that contains the specific diameter of the generating circle as fixed point over which the entire linkage pivots, and the center of the generating circle. Remember, in the physical implementation, there will be another rod over here. It will run somehow like this way. It will be fixed to this point, so in order to make sure that this point moves. But we are not after the physical implementation, we're after the mathematical model. In this mathematical model, we do not need this rod. It just obscures the mathematical essence of what is going on. But the mathematical essence of this particular motion, of this particular configuration, of this particular object is this: OD prime times the cosine of theta is OD. The angle theta is right here, and that shows that the point D prime is such that the point D is the orthogonal projection of the point D prime, which precisely proves that the trajectory of the point D will be, of course, some finite line segment. It will be a finite line segment that runs somehow this way. The point will oscillate this way, but the important thing to understand is that this motion of the point D is idealized motion, and the idealized mathematical model is not any sort of an approximation. This is exactly a straight line. As we saw, the mathematics of the Peaucellier-Lipkin linkage that we just discussed is nothing really, nothing fancy. It is at the level of an average upper middle school, lower high school plane geometry curriculum, and it is plausible that a motivated student, it doesn't have to be this specific age, but pretty much any human being who possesses that much knowledge about planar Euclidean geometry at the level of, let's say, average upper middle school, lower high school curriculum, can come up with this specific configuration of objects and generate a relevant proof that the trajectory of the point D in this case is a precise, mathematically precise straight line. But if such a person has an intellectual capacity to come up with all these things, this person will inevitably ask the following question: is this a flaky mathematical coincidence, or there is a deeper mathematics behind it? And we already know through the series of theorems that we proved earlier in this course that any circle that does pass through the center of inversion is taken by the corresponding inversion of the parent plane, be the power of that inversion negative or positive, into what? Into a straight line that does not pass through the center of inversion. And conversely, remember that when we equip the parent real plane with the point at infinity, our mapping of the real plane onto itself became a bijection, and that means that every straight line that does not pass through the center of inversion is taken into a circle that does pass through the said center of inversion, again, regardless of the power of inversion, be that power positive or negative. Here I evidently portrayed the case when the power of inversion is positive. When the power of inversion will be negative, we simply take that image of the straight line or of the circular arc and flip it over the center of inversion by pi radians, and voila. But fundamentally, we see that whatever we proved in the previous segment using nothing more than the machinery of the upper middle school, lower high school plane Euclidean geometry, that manipulation has a deeper mathematics behind it, and the fundamental idea of the mathematics behind it is precisely this property of inversion, which, by the way, means that topologically, from a topological standpoint, circles and straight lines are equivalent or equivalent topologically. And not only that, but we are equipped with all the knowledge and all the know-how how to deal with such situations. That is, using nothing but the Euclidean tools alone, a compass and a straight edge, we can be given any arc, such as the sample arc shown on the right side of your screen in red with the points that delineated, let's say, smaller arc, and we can construct the image of that arc with Euclidean tools alone, it will be corresponding line segment. But you see, this line segment belongs precisely to a straight line, which is not an approximation of any kind, but a genuine, mathematically precise object to which we refer as a straight line. And conversely, a straight line, if we're given a line segment that belongs to a particular straight line, we can flip it back with Euclidean tools alone. We have the know-how, we know how to do it. Compass, straight edge, we can flip it into the corresponding circular segment shown over here in red. This is a bijection due to this wonderful geometric transformation which we are studying in this course, and which is any inversion of the real plane with respect to a circle. We know the points that delineate this arc will be taken into the corresponding points over here, this way, this way, this way, this way, in any direction, and voila, we have a wonderful, deep theoretical explanation of why, not only how the Peaucellier-Lipkin linkage works, but we know why it works that way. Let us drill down a little bit and loiter around this statement. We saw that in the previous segment, we computed the distance OD in terms of the locally variable material. So now we will construct a product between the distances OC and OD. Let's write it down over here. OC times OD is equal to the distance OC is what? Twice R times large L squared minus small L squared divided by 2R, cancel. This comes out to L squared minus L squared, and this is a constant real number. Constant real number. You see, this is a constant real number. This is a constant real number. Their squares are constant. Their difference is constant, and that is the embodiment of the fact that the rods or the links shown in green have fixed length, and the red links or red rods that form a rhombus also have constant length. So this is a constant number. Now let us construct a similar product for the situation, for the point in time where our linkage is caught in an arbitrary deviation from the logical position of equilibrium that corresponds to the angle theta. So what we will have? We will have exactly the same thing. Look at this. The distance OC prime is twice R times the cosine. So it will be 2R times cosine of theta times L large squared minus L small squared divided by 2R times the cosine of theta. And what do we see again? Look at this. This quantity and this quantity cancel each other out. And what do we have? We still have L large squared minus L small squared. This is still a constant real number, and not only it's a constant real number, but it's a constant real number that matches this constant real number. So we have this product and this product is exactly the same. So that is why we can say for any points C and D, it is the case that this product equals to this product. So what is this? What is this quantity right here? Well, this quantity will be evidently the square of the radius of inversion. Exactly. So we will write it down like so. L large squared minus L small squared is equal to R small squared, where R is the, well, we'll put it this way, is the radius of inversion of the parent plane with respect to the corresponding circle. We know that. And it also captures, it also tells us what the power of inversion, and the power of inversion in this case is what? Positive or negative, and why? Positive because precisely L large is strictly larger than L. So this difference is always positive. So there's always the plus sign over here, plus sign. So the power of this inversion is positive, and this relation shown over here actually has a very straightforward what? Geometric interpretation. We already see what is going on over here. This is the, if we move the smaller term L small squared to the other side, we will have our Pythagorean theorem. L large squared is equal to L small squared plus R small squared. And what is the geometric interpretation of this? Well, it is easy to figure it out. Let me do that for you right here. So what do we have? The geometric interpretation. Where do I have the room? Let's say I have this room over here. So this situation is captured geometrically, again, using the colored links or rods of our Peaucellier-Lipkin linkage correspond to the following situation. So we have this and this going on like this. Then we have this distance right here. And then we have two of our links like so. So you see, this is right here, and right here. So this distance is L. This distance is uppercase L, lowercase l, lowercase l. The angle over here is evidently right. And what is this? This is precisely R. This is the radius of inversion, and this is the geometric interpretation of the algebra of this particular situation. L small squared plus R small squared, R small, L small, hypotenuse, two sides, and voila. In other words, if our contraption somehow collapses into the straight line, so in other words, our rhombus degenerates, the points C prime, M prime, and D prime collapse into one point, this point right here. This is the guy. Then we have our situation, and typically this will be what? With the image, it will be an isosceles triangle, but small triangles wise, this will be two right triangles, and this is the interpretation of the radius of inversion. In other words, if we picked our lengths uppercase L and lowercase l using the condition, this one right here, you see, in some sense these numbers are arbitrary, but after that our numbers are locked in. There is technically, for the magnitude of R and R squared, the radius of inversion is fixed. So the circle of inversion, let's say I will portray it with yellow, will run, I don't know, somehow this way. So with respect to the circle, the circular arc, you see that the point C traces it over the circle that passes through the center of inversion. This is the point C. Where is it? The point C runs somehow here, 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 here. This is our point C, 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 and C. As this point runs over circular arc, the output point, the point D, traces a straight line that is perpendicular to this diameter of the generating circle that passes through the fixed point. Remember the mechanics of how we generated the proof of our theorem. There was a straight line, and then we took it from there. We used the similarity of triangle, the workhorse formula of inversion, and that's how we generated the proof that a circle, in this case, that passes through the center of inversion will be taken into a straight line that does not pass through the center of inversion, and conversely, and this is it. So now we can make the following four observations. Let's carefully enumerate them. If in our linkage that is shown over here, the classical incarnation of Peaucellier-Lipkin linkage, the power, the input power, is applied to the point C in such a way that the point C traverses an arc of a circle that passes through the fixed point O, then the output point D will travel along a straight line precisely, and conversely, no one prevents us from designing our linkage in such a way that the input power is applied to the point D, and the point D in such a way that the point D traverses a straight line. Then what will happen? Well, we know already the output of this linkage will be the point C that traverses an arc of a circle that passes through the fixed point O, and according to our calculations that we did, OC, OD, we can calculate all sorts of interesting quantities, but this is already not of interest to us in this episode. That is one thing. So circle for C, straight line for D, straight line for D, circular arc for C technically. And here we also see why the arc that we consider here, that is traced by a something in the physical implementation cannot pass through the center. Well, the center of inversion is taken into the point at infinity, so it doesn't really, it's not possible in the physical world to make sure that the point C passes through the through the center of inversion, because then we will have a mechanism that runs into infinity, and there are no infinitely available resources in the physical world. But despite that, we do understand now, since we see how the mechanics of the Peaucellier-Lipkin linkage unfold, how it weaves its magic, we understand that there is nothing inherently or theoretically limiting about the amplitude of motion of the point C. We know that regardless, theoretically, regardless of where the point C on the circle that passes through the center of inversion, its image will belong precisely to a mathematically precise straight line, and conversely. But in the physical world, of course, we exclude this point over here. So if we have lengthy materials, then we can increase the arc, but regardless, small arc for the point C, precise straight line. Medium arc for the point C, precise straight line for the output. Larger arc for the point C, still precise straight line for the trajectory of the point D. And one more observation, we know we can flip things around a little bit. What does that mean? Well, we can exchange the roles of the points C and D. Let's assume that the point D now, instead of tracing a straight line, it traces an arc. So let's say here we'll have like this. The point D right here traces an arc. Point D traces an arc right now. This arc right here of the circle that passes through our fixed point O. Well, then in this case, if we delineate it somehow this way, then we will know that through the corresponding inversion, this point will be taken into where? It will be taken into a line segment, you see, this way. So our point C will run around this line segment, and the point D will run over the circular segment. So the statement that we make over here in conclusion is the following. If our, let's say, maybe in some sense, inverted Peaucellier-Lipkin linkage is put together in such a way that the input power is applied to the point D in such a way that the point D traces an arc of a circle that passes through the fixed point O, then the output of such a linkage will be the point C that runs along a mathematically precise straight line. And conversely, if we apply the power to the point C in such a way that the point C runs along a straight line, then the output point D will traverse an arc of a circle that passes through the fixed point. So this is also an interesting take, an interesting variation on the classical Peaucellier-Lipkin linkage. So we have this point into here, this into here, this point into here, and so on. And in order to show you how this particular, let's say, inverted Peaucellier-Lipkin linkage will work, again, I have put together for you an animation using the free software called GeoGebra, and in that animation, again, you will see that the point D, in this case, I pretended that the power is applied in this inverted linkage to the point D that traverses a certain circular arc that belongs to a circle that passes through the fixed point, and the point C runs around first, giving you a chance to exercise your visual mathematical intuition without any tracer. But then I turn the tracer on for the point C, and you will see that that point will actually traverse a segment that belongs precisely to a straight line. This is it for the problem 25 and the practice session number 6. And as a fair warning and a heads up for the next practice, bring your knowledge of the Japanese language. I'm just kidding, because in the next practice we will solve a problem that deals with the so-called sangaku. And this problem apparently dates to the year of 1788. And in this problem we will be given let's say 3 generating circles: the outer generating circle of known radius and 2 smaller circles that are built on the diameter in such a way that this circle is exactly 1/2 of the radius of the larger circle, and this circle is also exactly 1/2 of the radius of the larger circle. These 2 circles touch each other externally, and they touch the outer generating circle internally, here, here, and here. And then we have 2 families of inscribed circles: the family of blue circles and the family of red circles. The family of blue circles is constructed as follows. All these circles, they touch the outer generating circle internally from the inside, and the first such blue circle touches both of the smaller generating circles externally, and then every one blue circle is inscribed in such a way that it touches its immediate logically previous blue circle externally, the one of the generating circles externally and the generating circle internally, and then smaller circles are inscribed that way. And the family of red circles is inscribed in a yes, I know it is a very rather convoluted family of inscribed circles, but the family of red circles is inscribed in such a way that the first circle, red circle, it touches the smaller generating circles externally, and the blue circle externally also. And then every such circle also becomes smaller and smaller, and it touches the next 2 blue circles externally and the smaller circle externally too. And these red circles are inscribed with every consequent number, 1, 2, 3, 4, 5, in such a way that they also touch 2 immediately adjacent blue circles and the smaller generating circle, and they grow smaller and smaller in radius. And the objective in this case will be, if we are given, let's say, r is the radius of the larger generating circle, we are to express the radii of the blue family of circles and red family of circles in terms of this radius of the generating circle and the ordinal number n, 1, 2, 3, 4, 5, and so on.